Hello everyone, this is Dr. Surya. Today we are going to see about how to draw the velocity triangle of Kaplan turbine. So before going into that, we'll have a small introduction about axial flow reaction turbine. So if the water is flowing parallel to the axis of the rotation of the shaft, then the turbine is known as axial flow turbine. And during the flow of water, when a part of pressure energy is converted into kinetic energy, then the turbine is known as reaction turbine. Okay, so this axial flow reaction turbine, the shaft of the turbine will be vertical one and vanes will be fixed on the hub actually, hub or bars, we call it as hub or bars, and this lower end of the shaft will be called, it will be made larger and it is called as hub. There are two important type of axial flow turbine. One is going to be the propeller turbine and another one is going to be the Kaplan turbine. So in propeller turbine, vanes will be fixed to the hub and they cannot be adjusted. And that kind of turbine is known as propeller turbine. And if the vanes of the hubs are adjustable one, then that is going to be the Kaplan turbine. Now we'll move on how to draw the velocity triangle of a Kaplan turbine. So this is going to be the guide blade of the Kaplan turbine. So the water is flowing laterally into the guide vanes and it is getting deflected by the guide vanes and it flows axially through the propeller. Okay, because it is an axial flow reaction turbine, so which is that water is entering laterally. So water is entering laterally. So likewise I am drawing this and let this V1 be the velocity of jet of water. So we are denoting the suffix 1 to be the inlet and suffix 2 be the outlet. So water is entering laterally. So I am drawing this V1. V1 is going to be the velocity of jet. Okay, so when the velocity of jet is entering with an angle, so this consists of an angle, and as we have learned in our engineering mechanics, so this V1 can be subdivided into two of components. That is going to be the horizontal component, that is the VW1, and next will be the vertical component, that is VF1. Okay, so VW1 is going to be the whirl velocity. We call this as whirl velocity, that is component of the velocity of the jet in horizontal direction. And VF1 is going to be the velocity of the flow, and this is going to be the component of the velocity of the jet V1 in vertical direction. So we'll draw this one. So this be the horizontal direction and let this be the vertical direction. So this be VW1 in horizontal direction and VF1 in vertical direction. And because it is making an angle, I'll draw this and I will write it as alpha. Okay, so alpha is this flow velocity, I'll keep like this, and alpha is going to be the guide blade angle. So which is nothing but the angle between the direction of the jet and the direction of motion of the blade at inlet. That is going to be our alpha. Okay, so we have one more velocity, that is velocity of the blade, because blade will be rotating with one velocity. So generally water is having more force, that is our velocity of the jet will be having the more force compared to the velocity of the blade. That is, the velocity of the blade U1 will be always less than the velocity of our jet. Okay, so I can draw this velocity of a blade here. So let this be U1 and this velocity of the blade, and if I am connecting this, and this will become this is my U1, that is velocity of the blade, and another one velocity is called as the relative velocity, that is going to be my VR1. And you have this is also making an angle, and this becomes, this angle be theta. So theta is going to be the blade angle at inlet. Okay, theta is blade angle at inlet. Okay, so U1 is going to be the velocity of blade. and this is going to be the inlet velocity of our Kaplan turbine. Now we have to draw the outlet velocity triangle of the Kaplan turbine. Again, this is going to be very simple. So as said earlier, water is entering the turbine laterally and it is getting deflected by the guide weights and it will be flowing axially through the propeller. So the flow is going to be in axial direction, which means I have to draw like this. That is, my alpha will be equal to 90 degree in case of my outlet triangle. Okay, so because it is going to be 90 degree, I don't want to resolve the component as horizontal component as well as vertical component. There will be only the velocity of the blade as well as my velocity, relative velocity. Only those two things will be there. So this is going to be my U2 will be my velocity of the blade at outlet, and which connects this velocity of a blade and my V2, that is my velocity of the jet, that is my V2, that will be my VR2. It's going to be very simple. Okay, so again I repeat, and this is going to be the outlet velocity triangle. So the water is entering tangentially or laterally and it goes out as axially. That's why my alpha value is 90 degree at the outlet velocity triangle. Since it is at 90 degree, there is no necessity to subdivide into horizontal component and our vertical component, which means there is no VW2. This VW2 will be 0. Okay, this is a major thing you have to remember here. Only if you are having certain angle, you will be resolving it into horizontal component and the vertical component. Since it is in 90 degree, there will not be no horizontal component and there will not be any vertical component also. Okay, so that's why no need of solving that horizontal and vertical component, and my VW2 will be 0. So this is the velocity triangle of a Kaplan turbine. Hope you have enjoyed this. Happy learning and thank you.